Test, test. Okay, got another problem here. This one is about a sinking sphere with a drag force, and it's using Lagrange equations and Jacobi integrals and Noether's theorem, and it's from Classical Mechanics Midterm 1, Problem 3. So the first thing, I guess let's read the problem. A sphere of mass m is released from rest into a vat of liquid, sinking under the influence of gravity in a viscous drag force, so that its equation of motion reads z dot dot plus gamma z dot minus gravity is equal to 0, where this gamma is equal to beta over m, and it's a constant. And beta is likely related to the surface area of the sphere, but that's not plot. So the first thing we have to do is show that this equation of motion here can be obtained from this Lagrangian. Okay, so let's get started. So to find the equations of motions, we just have to use the Lagrange equations. Looks like this. So the partial of L with respect to z is equal to times g, and the partial derivative of L with respect to z dot is equal to, and then we have to take the time derivative of that. So you have to use the chain rule. Okay, now we put those things together. Oops, that's a mistake here. This should have this term here should have what should it have? Gamma. Yeah. Take the derivative of the exponent as well. Okay. So if we put those two pieces together, we get, pull out the exponential, gamma times z dot plus z double dot minus g is equal to 0, and can divide by this exponential on both sides, and we get the equation of motion. Okay. That part was easy. Now the next thing we have to do, number 2, is compute the Jacobi integral of this Lagrangian and verify explicitly that this here is true. Okay. Everything's working. Number 2. The Jacobi integral is defined as this quantity here in general. It's the sum over the velocities times the Lagrangian with the partial derivative of the Lagrangian with respect to the velocities minus the Lagrangian itself. And so in this case, they write h as a function of z dot, and t, because, well, the Lagrangian is a function of z dot, and t. And so in the sum, we only have one k. So we only have z dot times the partial derivative of Lagrangian with respect to z dot minus L of z dot t. Oops. This part here, we just found that. This is there. So h is equal to e to the gamma t z dot squared minus Lagrangian again, which this is 1 minus a half, so h ends up being 1/2 z dot squared minus gravity. Okay, now we have to take the complete time derivative of that and show that it's equal to the partial time derivative of the Lagrangian. Okay, and when we do this, we have to be a little careful because when we're doing the full time derivative, we have to remember that z dot is a function of time, and so is z. So do that. First, gonna take the derivative of this and leave this constant, and then I'm gonna take the derivative of this and leave this constant. So z dot is a function of t, so this becomes 1/2 times 2 z dot times z double dot minus g z dot. Okay. Clean this up a little bit. Now the key is that we want to try and use this equation of motion that we found in part 1 in here so we can get rid of some of these terms. So I'm going to rewrite this equation of motion down here. The double dot plus gamma c dot minus g. And if we did this correctly, the big F, this guy here can rewrite as gamma z dot squared minus 1/2 gamma z dot. Okay, and then the rest stays the same. And this now all the terms that have a z dot, we can pull one out. So, well, these three. So that's gamma z dot plus z double dot minus g. And then that's the equation of motion right there that we pulled out. So that's equal to 0. And what we're left with is the terms that I didn't touch. So minus 1/2. Okay, so that simplifies a lot. So we have that the total time derivative of h is equal to, can pull out the minus gamma into the gamma t, 1/2 z dot squared plus g c. Okay, so I factored out, I did some algebra here to basically get this term, and that's equal to 0 because that's the equation of motion, and that simplified this total derivative of the Jacobi integral down to something like this. And now we just have to take the partial derivative of the Lagrangian with respect to something, time, and with a minus sign, and show that that's equal to that. And if it's not, then probably made a mistake, but pretty sure it is. So it's equal to minus, find the Lagrangian again. And this time it's just a partial derivative, so we don't have to worry about this stuff. We just have to take the partial derivative of that, which is equal to the exponent itself times the gamma with the minus sign. And that's exactly what we had up here. So yeah, the key is using the equation of motion to get rid of some stuff in the derivative, and then you can verify that explicitly. Okay, moving on. Number 3, prove that the action is quasi-invariant under the infinitesimal translation z goes to z prime, which is equal to z plus epsilon. Okay, some more pages. Okay, so z of t goes to z prime of t prime, which is equal to z of t plus epsilon. And what you can also infer from this actually is that t prime remains unchanged, because here it's t, so they don't tell you that, but and that'll be important later because that means dt prime is equal to dt. Okay, so oops, okay, now derivative. So to prove that something is quasi-invariant under an infinitesimal transformation like the one that we have in this problem, you have to assume that there exists a function called, they call g of, and it depends on the generalized coordinates and time, such that if you take the integral over this new Lagrangian, the prime Lagrangian, which depends on the prime coordinates, and you subtract the original Lagrangian, the integral of the original Lagrangian. So in the book they use q as the generalized coordinate, but I'm using z already for this problem. So plus epsilon times the time derivative of this function, which in our case is going to depend on z and t. And you take the integral of the prime Lagrangian minus the integral of the original Lagrangian plus this additional part that involves this function g. And if you prove that this is equal to 0, then you've proved that this transformation is quasi-invariant. And then later on, there'll be a conserved quantity associated with this transformation that we'll get to in a later part. So first, let's find what the prime Lagrangian is under this transformation. So for the Lagrangian, we need go back down to Lagrangian again. So the original Lagrangian, which depends on z dot, and t. And okay, so we need this one is easy because so z prime is equal to z plus epsilon, and z prime dot is just equal to um, z dot, because epsilon is a constant. And like I said earlier, t prime is just equal to t. So now we can write the prime Lagrangian in terms of the original unprimed coordinates. So this is equal to dot prime squared plus g equal to g. And here all we have to do is add this epsilon. Okay. Okay, so now we have to use this big equation here involving the two integrals. So first the integral over the prime Lagrangian minus the integral of the original Lagrangian test. Okay, I had some problems with my Zoom like usual, but I'm just gonna pick up right where I left off. So we are looking at this equation here, trying to find this function g. So if you look at this, a lot of the stuff cancels out. All of this stuff here they have in the second term too, so and there's a minus sign, so that all goes away, and you're just left with the integral and what's left in this integral, epsilon d time derivative of g is equal to 0. These epsilons can cancel out, and this here is the this is the integral of the derivative of g. So if you take the derivative of g and then you take the integral, you're just left with g. Minus g. Three. And the integral of exponential is get a factor of 1 over gamma. and to be, can add integration constant C if you want to here. It'll get absorbed into a different constant later, but if you like having the constant there, you can add it now. And so see that this function doesn't actually depend on Z this time, it only depends on T, but later, if there's other transformations, which there are in the later part, it could depend on Z as well. Okay, so let's see where we're at. Yeah, so we know that there's a function G now to make that equation true. So we know that the action is indeed quasi-invariant, and now we just have to find the associated constant, constant of motion associated with that transformation. To do that, we're going to use another formula that looks like this. The associated constant of motion is equal to sum over all the velocities again. I dot x, I'll tell you what x and I are in a second. X plus g. Okay, so the way they define these x and phi is the time, the x is related to the time transformation. And okay, so we know that in our current transformation, t prime is just equal to t, which means that x is equal to 0, and qi goes to qi prime of t prime, which is equal to qt epsilon qt. Okay, so we only have one generalized coordinate, so t prime goes to z of t epsilon, which means in our problem I is equal to 1. So using these two results, we can go back up to this constant and say that, again, the partial of L with respect to z dot times z dot times x, which is 0, minus 1, minus L times 0 plus g. So we have to find what this is again. Up here, there it is. And then to find what g is, and this is what I was talking about with this constant. So g is equal to little g. And now this constant can just be absorbed over here in this constant. So just get rid of that. We're left with negative Okay, and so this is the constant. Uh, they in the problem they call this constant J1. You can call it whatever you want, and you can just rewrite it to get it how they have it in the problem. Yeah. Yeah. So what did we do? We proved that this action is quasi-invariant, and we know that this is the constant of motion associated with that translation. So now we're just going to do the exact same thing again. This time it's just going to be a little harder because this phi that was equal to 1 up here is now equal to something a little more complicated. But it's just going to be the exact same thing. So z goes to z prime of t prime, which is equal to z of t. So again, we know z of t plus epsilon e to the negative. So this x is still 0, like I said, and this phi is equal to e to the negative gamma t. And again, we need z prime dot again. So we need, well, actually we need z prime dot squared in the end, but first we have to find z prime dot. That's equal to z dot plus epsilon e times negative gamma. Okay, now here when we square this, there it's something kind of subtle that you have to do. So you're gonna get another term here that's epsilon squared, gamma squared, e to the negative 2 gamma t. Now this term here, you could keep it, but if you do keep it, you're not going to get the answer that they want. And what I'm pretty sure you're supposed to do is this epsilon is already, it's an infinitesimal small translation. And so if you have something that's really small and you square it, you get something that's even smaller. So this term here, I'm saying, is going to go to 0 because I'm ignoring terms that are of order epsilon squared or higher, which means that the z dot prime squared that I'm keeping is just this. And so With that, we can again write the prime Lagrangian is equal to uh, t is equal to t prime again. 1/2. Okay, my Wi-Fi went out again, but I'm really hoping that it's gonna keep recording the previous bit, so I'm gonna keep going and hope for the best. Okay. If not, I'll come back and redo that bit. Okay, so hope that doesn't happen again. It's pretty annoying. Where was I? 2 z dot epsilon gamma. That's the prime Lagrangian. And I'm gonna just expand this out completely. Oh, this one has to be outside. These exponents are gonna cancel each other out. And this should be z dot, it should just be z. And this should all. Okay. So again, we're gonna use this formula. And hopefully a lot of stuff will cancel out again like last time. Uh, That was the unprimed Lagrangian. And here's a G function. So that cancels with that. That cancels with that. You're left with negative C dot epsilon gamma plus G epsilon. They'll have epsilon again. And again, the integral of the derivative of G is just G. So G, this time it will depend on Z. So this is just the integral of Z dot is Z. And again, there's a constant there, but we know that that's going to get absorbed into the constant of motion. So this is G. And now again, constant of motion, which they're going to call J2. Equal to x still 0, but this phi is not 0. Phi is e to the negative gamma t plus rg. And this partial derivative, I'm pretty sure I know what it is, but I'm just gonna check one more time. Yeah, it's v dot times the positive exponential times negative exponential, and then minus these exponentials will cancel each other out. And so this is constant motion we get for the second transformation. And there you go. They get the same thing. So which because I get the same answer as them, to me confirms that you just ignore this term that we had earlier. Okay, so now they want us to combine J1 and J2 show that the general solution of the equation of motion has the form. So just solve J2, I'm gonna rewrite J1 down there. Oh, I forgot already what it was. So the way I'm gonna try and combine them is that this J2 equation has z dot, so I'm going to solve for z dot in this one and then plug it into J1. So z dot is equal to J2 plus no, there's supposed to be minus sign here. Plug that into the J constant. Like that. And then I just can do some algebra. And then, so this no longer depends on z dot now because that's what will be plugged in. And now we just, what are we doing? Solving for z. And then once we've solved for z, we're going to plug it z back into the equation of motion and just verify that that's correct solution. And ran out of time again, so 10 more minutes in this meeting, so I'm gonna try and finish this problem. And then just to rewrite how they have their final answer. Okay, that's beauty. Now we know that J1 and J2, they're both constants. So that means that J1 dot is equal to 0 and J2 dot is equal to 0. Because by definition, they're constants, and if you take the derivative of a constant, it's equal to 0 with respect to time. So that should make taking this d dot derivative pretty easy. 1 over gamma g minus 0 minus another constant 0 minus j1 e to the negative times equal to 1 over gamma g plus gamma j1. Okay, I'm gonna take another time derivative. Okay, now we have to, the equation of motion was d double dot plus gamma c dot plus g is equal to 0, so d double dot is negative gamma j1 e to the negative plus, that was c double dot plus gamma c dot is and then plus g. Oh my goodness. This is equal to let me rewrite that. I didn't do a very good job here. Test. Okay, there was actually nothing wrong with this equation of motion. Well, actually, this was just supposed to be minus g. So and you can see that that's gonna give exactly 0. Okay. Okay, so we verified equation 4, the equation of motion. We have solution for z. We know what the constants of motions related to these two transformations are. And last thing we want to do is find the sphere's terminal velocity. So as it's sinking, it's initially at rest, then it's gonna accelerate due to gravity, and then at some point the force of gravity and the uh, friction, the drag force, are gonna be exactly 0, so the net force on the sphere will be 0, and there'll be no acceleration. In other words, z double dot will be 0. And when z double dot is 0, there'll be some constant velocity that the sphere is sinking at, which is called its terminal velocity. So if the mass is released from rest, that means at t equals 0, if we'd say that defined, yeah, so starts at z equals 0, and because it's released from rest, the dot is equal to 0, and we know that initially it's accelerating with gravity. Okay, so what does that mean for these constants? So J and J2 are constants, which means that whatever they are at t equals 0, that's what they have to be at all the later times when t is greater than 0. So J at t equals 0 is equal to J1 anytime later as well. So what is J1 at t equals 0? Well, we have to remember what J1 was. J1 is equal to one over gamma exponent G minus gamma. Well, T1, J1 at t equals 0, e to the 0, G minus 0 gives G over gamma. And so and what about J2? Well, that's equal to at 0, z dot is 0, z is 0, and t is 0. So at j2 at t equals 0 is actually just equal to 0. And okay, I'm not sure if we actually had to do all that because we already know that when the sphere reaches terminal velocity, z double dot is equal to 0. So actually we could have just used the equation of motion minus g is equal to 0. So we see that the terminal velocity is equal to g over gamma, which we also just found to be j1, and it's constant. So that makes sense to me. The terminal velocity depends on gravity because that's the force dragging it down, and the force pushing, keeping it back up is related to the constant. So that's that, and that's the end of this problem. I hope this was useful. Thank you very much for watching. Goodbye.